Screen is yours, Janos.
Let me check if it's going well. Yeah, okay. Thank you. So let me thank you, first of all of you for coming to my talk. And I would also like to thank the organizers once again to invite me to give this talk. It's a great pleasure to be part of this event. I will talk about a recent paper about repeated games with countably many players and tail-measurable payoffs. And this is a joint work with Galit, Arkady, and Ailon. And just based on the title, you can already see the connection to the previous talk by Galit, because I will also talk about repeated games. And I will talk about tail-measurable payoffs. The new ingredient is that the number of players is not necessarily finite, but typically maybe this will be countably infinite. And this brings me to a little bit more precise comparison here. In Galit's presentation just before me, one of the theorems, the existence theorem for Epsilon Equilibrium, said that the set of players was finite. The action set of each player was finite as well. The payoffs had to be bounded, Borel measurable and tail measurable. Galit put, I think if I remember correctly, the adjective or qualification Borel into the game. So it was called Borel repeated game, but anyhow, it's a Borel measurable function. And if it's all true, then the game admits an epsilon equilibrium for every positive epsilon. As Galit explained in details, the proof was based on regularity of the min-max values of the players, because it's possible to approximate the winning sets from the inside with compact sets. So just it's just a preview of the talk here. In this talk, in this paper, the existence theorem will look similar, but now the set of players is not necessarily finite, but it can be countably infinite. So I think it's even more interesting to assume from now on that it's countably infinite, because I do not have to distinguish continuously between finitely many players and countably infinite many players. So the set of players is the set of natural numbers, for example. Now, in this case, we have the regularity that Galit talked about in the previous proof. It doesn't apply anymore, and we are using different techniques to prove this theorem. So I would like to give a little bit of a motivation for infinitely many players, but also basically for this paper. For those of you, I don't know everybody's background exactly, but I'm sure many of you have seen games with infinitely many players. There are various motivations to look at such games. For example, we refer to the paper by Mark Fornefeld later on too. He enumerates quite a few of these, and I will also go through a few of them. But of course, this list is very far from complete. So what can you think of when we are talking about infinitely many players? Well, in some models, in some situations, this is actually an abstraction in which you are modeling an interaction between a large number of agents or players. And this number is perhaps finite, but it's large in a sense that by looking at an infinite player set, you can nicely approximate it and derive results. I would like to draw the usual analogy also to the time horizon. In these games, the time horizon is very often infinite. There, it's also the case. Is it really true that the game has infinitely many stages? But it's very often an abstraction in models. So I will not talk too much about all these models here, but I will mention a few. For example, in the economic literature, there are models with overlapping generations. It has its own literature. They even short shortly, briefly, they call it OLG, the overlapping generation games. So this is, for example, to explain macroeconomic dynamics, and it's a framework for that, or economic growth. Typical situation is that an agent lives a finite length, so it's a finite lifespan, but it's sufficiently long in such a way that his lifespan will overlap with the lifespan of some other follow-up players. So you can think of generations, and then you can study in an economic setting, for example, how to allocate resources across generations, or you can analyze simply the life cycle of us. In the beginning, we are studying, we are investment in human capital, and then we work, we retire. So what's happening in all these stages? In some models, there are interactions between long-run players. You can think of long-lived firms and some sequence of short-run ones, for example, a sequence of customers, large networks. Maybe I mention one more and then I stop. Time on inconsistent decision makers. So in this case, actually, there is only one decision maker, but his or her preferences are not consistent regarding time. Think of somebody who wants to stop smoking. So maybe it's me. I'm not smoking, but just suppose I want to stop smoking. You could imagine that for today, my most preferred strategy would be to smoke today my last cigar, and then tomorrow I stop smoking. And at least today I can enjoy it. But once it becomes tomorrow, then I will have a second thought and decide, well, wait a second, maybe I will smoke my last cigar tomorrow and then stop the day after. So my preferences will change from time period to time period. And very often this is modeled by multiple selves. So it's still me, but a different self of myself. And then you get to a large number of decision makers like this. So when the set of players is countable, maybe it's an interesting thing to think about. The role of an individual players is still somehow there, right? It cannot be ignored. This is somehow in contrast in the literature when you have an uncountable set of players, non-atomic models. In fact, I'm thinking about Abraham a little bit, because Abraham, if I'm not mistaken, you worked quite a lot on cooperative games, right? With uncountably many players. So that could also be a model that I should have mentioned maybe. There's another motivation for this paper, not only to cover infinitely many players for this type of reasoning, but also the proof technique itself, which we believe will be useful for further results, but this I leave for Eilon. According to my information, it will enter his talk somewhere. So this is the agenda for today. Very, very straightforward. Everything is straightforward except the proof. So the model, this is following Galit's description, but we will have an infinite number of players in it. And please stop me if there's a question. I'm unable to see the chat. So maybe somebody can help me out if something comes in that I should address at that point, and then I try to answer it. So for the model, let's see, that's the first part. So what are we looking at? Now I will define repeated games in a more general way, and I will add the assumptions a little bit later so that I separate the assumptions a little bit from the general description. It will come very soon, but not yet. So it's a tuple in which we have a set of players, capital I. The players in it will be denoted by small I, and then each player has an action set. It's capital AI. It's the action set of player I, and each player has a payoff function, small f I. So once again, I is the set of players. AI is a non-empty set of actions for each player. capital A, as before, it denotes the action profile. So if every player chooses one action, then we get an element of capital A. It's an action combination. And then this is the payoff function for each player I. What does it do? It collects, it looks at the action profile at each stage. So it will be a sequence of action profiles, and then he attaches a payoff to this. Now, I would like to go through the timeline of the game a little bit slower because we have two infinities very soon. So the play of the game is as follows. At the play is game played at stages or time periods, if you want, in the set of natural numbers, which starts at 0. We start at time 0. The players choose actions. So player 1 chooses an action from his action set, player 2 from his action set, and these choices are made simultaneously. So this is resulting in an action profile or action combination, which will be A0, because this is for stage 1. This is revealed to all players, and then we move to time 1, stage 1, when the players choose actions again simultaneously, and this will result in an action profile A1 and so on. This will do indefinitely, and then all these choices of actions will give us a play or run, and the payoff of the players will depend on this. So player I gets Fi of this infinite run, and player I is going to maximize her own payoff. So now I'm just looking at if this is the right moment or the next one. I think I will do it here. So what I will do is, for the moment, it's not assumed yet, but I will assume that the set of, you can see the what I'm writing, right? Yeah. So for the moment, I will assume that the set of players is the natural numbers because it will come very soon. But I want to explain the timeline once again, because as soon as I assume that I is infinite, we have two infinities. The set of players is infinite, but also the set of stages is infinite. So I want to make sure that it's all okay. So in the beginning of the game, we are at stage 0. So this is the first time when the players will do something. And if you have infinitely many players, then there we have a player 0. We have a player 1, a player 2, player 3, and so on. So what does player 0 do? It chooses an action. It's A0, and it's the player index A00. Player 1 chooses A01, A02. And these choices that I'm writing here, these are made simultaneously. Sorry for the handwriting. I didn't have much space on the slide. And so all these choices are made simultaneously. And this is giving us the action profile A0. Then we move to stage 1, when the same thing happens, but now the players are choosing new actions. I just change the upper index. And then, of course, it goes on. And this will be also made simultaneously. And this will be the action profile that we call A1. And then, of course, we continue like this infinitely long. So what you see here, what I wrote down in this is like a very large matrix with infinitely many rows and infinitely many columns. And what you see here is nothing else than a run or a play. It's just an action for each player and for each stage. And did I want to say? Oh, yeah. So what if I put these two things together? Maybe I should use a new color with that I'm running out of colors. So if I look at these two stages, they together define a position for time period 2, right? Because we already know what happened in the past. So this will be the position for the next stage, because when we are here, then we have all these actions that have been chosen before. Okay. And then the player's payoff here will depend on this entire infinity by infinity matrix.
Janos?
Yes.
when you say that the payoff function is the Borel measurable and the tail measurable, then it's with respect to the time or the
Yes, I will come back,
players?
come to the assumptions in a second. This is the reason why I separated the two, because I think the timeline, who is doing what, and all the assumptions would be too much for one slide. So I will come to that right now. Yes, it's a very good that you asked, but this is coming up. It is going to have to stop sharing this thing now. So these are the assumptions. Now, from now on, let's assume that the set of players is indeed countably infinite. The action sets are finite. So everybody has a finite set of actions. And as Ron is just asking, the payoff function, each player is bounded and Borel measurable, but Borel measurable with respect to which topology? And this is what I will do in the next slide. This will be with respect to the product topology. And I will elaborate on it a little bit to make sure that it's, try to make it clear. Tail measurability is not yet in the model because we don't need to define the model, but I will assume it later. So I think this is clear, right? This is the set of players. This is a finite action set. Boundedness is a clear concept. So I will really go into this Borel measurability and this product topology. So now I will have two slides on the topological and measure theoretic background or setup of the paper. Those of you who are perhaps less interested in this topological or measure theoretic setup, or perhaps less familiar with this, they can just safely consider this slide and the next slide as a kind of intermezzo. After this, I will come back to the strategic aspects of the game, construction of equilibrium. This will be always there somehow, but the purely topological and measure theoretic part is concentrated on these two slides. So for those of you maybe can look at it as an intermezzo. So I will start with the topological part of it, and I will start from the most basic part of it, which is the finite action set of a player, AI. It's a finite set, so we just endow it with the discrete topology. It means that every set is open. Subset of it is open, sorry. The next step is the one where there's a crucial departure point from the model that Galit explained, and this is due to the fact that we have infinitely many players. Because if the players are choosing actions simultaneously, then we get an action profile. That's an element of A, but this has infinitely many coordinates. So it's an countably infinite product of finite sets. So now, which topology do we take on it? We take actually the product topology on the set of action profiles. And because it's an infinite product, this is in general smaller than the discrete topology, which would mean that not every subset of A is an open set. So if you have finitely many players, maybe two, then you would get the product of these two, and it's still a finite set, right? And in that case, there's no distinction here between product topology and discrete topology, but now there is. So we take the product topology. I go one step and I will explain the basis of this topology. And now the set of runs or plays is one action profile for each stage, for stage 0, stage 1, and so on. And this is also endowed with the product topology. And so what does it look like? Well, maybe you can also think of it as this. The basis of this topology is formed by the following sets. You take a player, you take an action. I should have denoted with the AI. It's not an action profile, but it will be clear from the text. It's an action of player I and a stage. And then we are looking at all runs or all plays where in this run, player I is playing action A at this particular stage. Now, okay, given this topology, Borel sigma algebra is well defined. And this is the induced sigma algebra. And as before, we call a payoff function Borel measurable if these inverse images, just as before, these upper level sets are element of the Borel sigma algebra. Now, the next slide on this measure theoretic part, it's about how to define strategies exactly. And it's nothing new in the literature. This is how it's usually done, but I want to emphasize the details. So what is a strategy for player I? Well, it still follows the natural intuition that the strategy should tell the player what to do in each position. So this is the set of all positions. T is the time, the stage, and then for each stage and if each possible path, the strategy sigma I for player I will give her a probability distribution on the possible choices, on the possible actions. And that's a strategy, but because of the fact that we have this uncountable set of action profiles, we need a measurability condition on this, which I call MC for short. And what does this measurability condition say exactly? It says that if you fix any stage, just fixed stage 10, for example, and you take one action for player I, maybe action 5 or whatever, then you are looking at the following map. The map has its domain, all the possible positions at this stage. So this is the set of positions that the players can be in stage 10. I took t equals 10. And this is the probability that in that position, player I will play action AI. So basically, given the position at time 10, you want to see what is the probability that you are playing a certain action. Now, this mapping should be measurable. And why this should be measurable, and with respect to the product topology on a to the power t, the reason is the following. Why do we worry about this? Why do we need this? The reason is, I have an example here, and I try to explain it slowly, and then we go back to more to the strategic and game theoretic aspects of these models. Let me go through here, and then I will make a drawing. Okay. So suppose that the action set is just binary. Everybody has two actions, 0 and 1. In that case, the set of action profiles is capital A. We have infinitely many players, so it will be 0, 1 to the power of the natural numbers. Now, this set, the set of action profiles A, has a set which is not a measurable set, because we took the product topology on A, and not every set is going to be measurable with respect to this. So take a non-measurable set and define a mapping sigma I. This mapping is not a strategy because it will only satisfy what I call a star over here, but it does not satisfy MC. So I'm not calling it a strategy, but this is just to explain what would go wrong if something only satisfies star, but does not satisfy MC. So the strategy, I already said strategy, it's automatism. The mapping sigma I, what it does is that at time 1, so not at the first stage, but at the second stage, he looks at what is the action profile that occurred at stage 0. And if this action profile is in this non-measurable set, then the strategy chooses action 1. And if this action profile is not in the non-measurable set, then it will choose action 0. Now, this is the time for me to make a drawing. And I think I have to move things on the screen a little bit. So I will make the drawing here. So this is stage 0. And the A is these are the action profiles for this stage, I make this is A. So this is just for stage 0. And then this has a kind of subset, a non-measurable set, which I called B. And what the strategy is going to do is that at stage 1, the strategy, if the action profile at stage 0 was in B, then it will play the action 1. And if it's in A, then it will play the action 0, right? So it's looking at the first stage, and depending on if the outcome is in B or not, it will play action 1 or action 0. So this is a situation in which this condition that I called MC is not okay, because depending on what happened at time 0, you are responding in a non-measurable way. So essentially, we are in general, we are not, there's no guarantee that we can calculate the probability of the set capital B under strategy profiles, because it's not measurable. And that means that we are unable to express in general what is the probability that player 1 will play action 1 in stage 1. So you can feel the gravity of this problem, right? How are we going to calculate expected payoffs in the infinite game if we cannot even express the probability correctly that the player is choosing a certain action at a very particular stage? So this is a well-known condition in the literature, but I wanted to make a point of it because this will come back in the construction. In the back of our mind, we always have to make sure that this measurability condition is handled with proper care. Oh, I forgot to take away. Can I delete what I wrote? Because otherwise it will keep it on. Thanks. If there's a question, please stop me. We go back to more. So, okay. So that now, it's assuming that we have correct strategies, meaning that they are satisfying this measurability condition, we can calculate with the usual machinery the expected payoffs for the strategies. So each strategy profile sigma will induce a well-defined expected payoff for each player I.
Yeah, Janos, I have a question.
Yes.
So if you assume tail measurability of your payoffs eventually, then
Yes.
you could in principle allow that they do something non-measurable in the first 100,000 periods, right? Because of the tail measurability, it wouldn't matter what they do.
It's still a problem because then you are restricting the strategies, right? Because even for the first stage, if something non-measurable happens, the strategy can respond to what happened in the past. This was exactly the problem in my example. It only went wrong for the measurability for the very first stage, but the strategies are responding to the past. So what you say, you have a point, but then the strategies, you are restricting the strategies in a very heavy way. Actually, I think it's still a problem. Yeah.
Because basically the non-measurability
it carries through the
carries into the future. Okay,
yeah.
Thank you very much.
Yeah, exactly. Like in the example I wrote, it's a very good point to your question, actually, yes. So now I will define epsilon equilibrium. The only change here is that we have infinitely many players, so I will denote epsilon with a vector. Everybody has his own or her own tolerance or mistake that she can afford to make. And what is an epsilon vector equilibrium? If you take any player I, he cannot gain more than epsilon. Her epsilon I by a unilateral deviation.
In the display, it should be epsilon I, yes?
Oh, yes, thank you. Yes, correct. It should be an epsilon I. Yeah, exactly. Yeah, first I defined it epsilon. I realized that it was not correct, but I forgot to change it. Yes, thanks. Yes. So now we go to the main result, and this will start with tail measurability. I don't think it will contain anything new compared to what Galit was telling, but I will repeat it briefly. then the main result of the paper, and then we will go into an example. Actually, the starting point is a beautiful game by Mark Fornefeld. His game is just a one-shot game, so it's not an infinitely repeated game. But I will discuss first this one-shot example by Mark Fornefeld, and I will discuss the repeated version of this game, because it's very nice to see, and it also gives us an intuition how the main construction is working. So what is tail measurability? I will be a little bit quick if you allow me to do so. A payoff function of player I is called tail measurable. If you change finitely many coordinates, then the payoff does not change. So if you have a run and you have another run, and if they only differ in finitely many positions, then, or stages, I should say, sorry, then the payoff does not change. So if I'm too quick, maybe somebody joined just now, then please stop me here, because otherwise I will just assume that it's fine. And Galit mentioned examples. I think she mentioned the long-term average of stage payoffs as an example of a tail payoff function, or the lim sup function. The discounted payoff, I remember that she indeed mentioned that it was not tail measurable. So we have tail measurability as an assumption very soon too. So what is the main theorem then? Consider a repeated game. What are the assumptions? Well, the set of players, as I already said, well, maybe I should have formulated finite or countably infinite, but I'm very much focusing on the part that so okay, finite or countably infinite, but for this presentation, I assume that it's already countably infinite already. The action sets are finite, the payoffs are bounded, Borel measurable, and tail measurable. So this is where tail measurability kicks in, and in that case, whichever positive vector epsilon you take, so each coordinate should be positive for every player, then there is an epsilon equilibrium. And maybe I could mention two examples here briefly. The first one is, I will mention this, although Galit also mentioned another example. So for zero equilibrium, we do not have any hope. It does not always exist. By zero vector, I mean that everybody's epsilon is zero. I take a very extreme case. I write here that there is only one player. You could imagine that the other players are also there, but they only have one action. And so basically they are dummy. So in this case, this only one player, what can he do? She has two actions. I call it A and A prime. And then she will choose one of these two actions every day. And then we can look at the long-term frequency of the first action. I denote it by FR of A. This is the first action. And well, if you look at this frequency, this will define the payoff. The payoff of this player has two cases. If the frequency of action A is strictly less than 1, then the payoff is exactly the frequency. So for example, if I'm the player, I'm playing A prime, A prime, and I play alternately, then my payoff will be equal to half, because that's the frequency of action A. But however, if I play action A with the frequency 1, then I get nothing. And well, in that case, of course, I don't have a zero optimal strategy. For every positive epsilon, I can make the frequency close enough, but if I make it to frequency 1, then I lose. So that's the example here. Now for the other example that I will talk about is actually Fornefeld's game. It's not only the example for what I write here, but it's a very interesting game, and also for the proof, it's a great illustration. So this will also show, among others, that if that tail measurability is playing an essential role in the proof, because if you drop it, then simply it will not be true. So if you don't have a tail measurability, then an epsilon, when everybody has the same positive epsilon, it doesn't have to exist anymore. And I will talk about von Neufeld's game a little bit, but what you have to keep in mind for the moment, and this is very important, this is a one-shot game that Mark von Neufeld introduced. And before I go to the repeated game, I really want to analyze this one-shot game in detail with you. So if something is not clear, please try to stop me. I understand the difficulty of the situation because we have infinitely many players and infinitely many stages in the repeated game. So if there's anything is not clear, I will try to explain something maybe differently. But now we are looking at Mark's game, which is a one-shot game. So it's played as follows. The set of players is still the natural numbers, and these players choose actions simultaneously, and the game finishes. In one stage, the game finishes and nothing ever happens there. The action set of the players is the easiest you could think of, only two actions for each of them, 0 and 1. And how Mark defined the payoff was the following. I need this set E. This set E will measure how many players are playing action 1. So in fact, this as an action profile will be in the set E if the majority of the players somehow the majority of the players play action 1. So how is it defined? It looks at the lim sub frequency of action 1 across the players. And if this frequency is strictly more than half, it's not important if I put equality sign here or not, so don't pay too much attention to that. But if it's strictly more than half, then we say that the majority plays action 1, and this is what we will use for the payoff function. So what is the payoff for player I? It's a minority game, so in the sense that each player wants to play the action that is played by the minority of the players. So let's do it more precisely. What is the payoff function for player I? And intentionally, I'm using the letter U, not F, to distinguish the one-shot payoff. Now, there are three cases that Mark distinguishes. The first case is that the majority of the players is playing action 1. In that case, if player I is playing action 0, then he's playing the minority action and he is winning then. If the majority of the players is not playing action 1 but action 0, and player I is playing the minority action, then player I is winning. And all the other cases that I have here, the otherwise case, this is the case when player I is playing the majority action, and in that case, player I is losing. So Mark has a lot more examples in his paper. He also refers to a paper by Peleg earlier on. So this is really a very nice paper if you are interested in games with infinitely many players, one-shot games. So the intuition I already explained, right, that the player I wins if she plays the action that is played by the minority. Here is an example. Suppose the players, they choose simultaneously, but suppose they choose 0, 0, 1, 0, and so on. So in this case, the majority is not playing action 1, but action 0, so it's not in E. So what happens to player 0? Player 0 is choosing the majority action, which is 0, so player 0 loses, player 1 loses, player 2 wins, player 3 loses, and so on, right? So these payoffs are bounded, and this set is a Borel measurable set for the topology described. Is it clear, this game? It's a minority game. I think that's the best intuition you can have for this.
I just wonder if the example of Peleg is not simpler in this context.
I believe that in Peleg's example, there was an epsilon equilibrium. But this is just my recollection. Because as I recall, Mark in his paper, he discusses also other examples, and this is the example that he really brings up as a counterexample to say epsilon equilibrium when everybody has the same epsilon. It's my recollection that in Peleg's example, there is an epsilon equilibrium. I think it was something like this. So in Peleg's game, I would have to look it up. I think Peleg was looking at a payoff where you not look at the frequency of the actions, but you look at how many players are playing a certain action. And if finitely many players are playing action 1, then something happens. And if infinitely many players are playing action 1, then something else happens. And in this game, it's substantially different in the sense that if everybody is playing the minority action with probability, that the action 1 with probability 1 minus epsilon, and the other action with probability epsilon, then actually everybody will win with probability 1 minus epsilon. But if you look up the payoff function and it turns out that I'm wrong, don't be surprised. But this is, I think, an epsilon equilibrium in that game. But maybe somebody else remembers the example immediately, but this is my recollection, Abraham.
Yes, I think that Peleg examples, okay, let's go on. But if you check that it has an epsilon equilibrium, that's fine. I think the example there is again 0-1 actions of each player.
Yes.
If infinitely many players are playing 1, then the payoff is if infinitely many play 1, the payoff is 1.
So I think the epsilon
minus it otherwise. Yes.
So I think the epsilon equilibrium is the following. I will try to write, but now I don't have the payoffs of Peleg in front of me, so this will be a little bit of.
If you claim that it has an epsilon equilibrium, then it's understandable why you move to this example. Yes.
So you play action 0
or 1
with or action 1. These are the two choices. And you only look at the number of players that play action 1. That defines the. So if finitely many players are playing 1, then you want to play action 1 because that's the minority. If infinitely many of them are playing action 1, then you want to deviate to action 0.
Correct.
And so here, if everybody is playing action 0 with probability 1 minus epsilon and action 1, then this is actually the good action because action 1 will be played infinitely many of them.
Yes, you're right.
But everybody is winning with probability 1 minus epsilon.
Mm-hmm.
So there's a, so I think I completely agree with you, Abraham. The relation between the two games is actually very close. But there's apparently a subtle difference that here it's really looking at frequency and this is only looking at the number of the players.
Okay. Yes, good point.
So Mark Fornefeld is arguing that there is no epsilon equilibrium for small epsilon in this game. And I think I will be able to go through the proof a little bit with you. Now, it's a one-shot game, so everybody can use a randomized strategy, mixed strategy, put some probability on action 1 and on action 0. So player I will use this randomization on her actions, and this will be the profile that the players are using at the single stage of the game. Now, given the strategy, this profile of I, we can look at what is the probability of this crucial set E. Now, as it turns out, this set has probability 1 or 0, and it's never in between. The reason is that this set E is a tail-measurable set. I want to avoid any confusion here, and therefore I emphasize that tail measurability does not refer to stages as before, but with respect to players. So it's in another coordinate segment of the function, but still with respect to players, it's a tail measurable set, because if you change finitely many coordinates, the frequency will not change, right? The simple frequency is independent of what a single player is doing. And because of Levy's or Kolmogorov 0-1 law, you can choose either. The set E will have probability 0 or probability 1. It's a symmetric situation, so I look at the case when E has probability 1, and then you can already sense that something will go wrong, because when does this set E have probability 1? Well, if you want a frequency at least half, then there should be at least one player, but actually there has to be infinitely many, who play action 1 with a decent probability, say actually probability at least half. So if you consider such a player, then he is playing the majority action with probability at least half. So this player will gain half by moving away the probability from the majority action and doing the other action. So the crucial point here is that a tail set, you cannot get the probability between 0 and 1. Either, you know, when there's a candidate profile Y, you already know with probability 1 if the majority of the action is 1 or not. Well, if you know it beforehand with probability 1, every player will know what to do. Everybody wants to choose the minority action, but if everybody does so, then that's not an equilibrium. Now I will go to the repeated version of Fornefeld's game, where in some sense we repeat this one-shot game infinitely often. So the set of players is unchanged. It's the set of natural numbers. The action set of players is still 0, 1, nothing changes. So essentially the stage game will remain the same. What is the payoff in the repeated game? Well, a player is either winning in the repeated game or losing. And the player is winning in the repeated game if she is winning in the stage game infinitely often. So essentially, after finitely many rounds, she will win all of them. So maybe I'm player 10. If I lose maybe in the first 5 stages, that's fine, as long as I'm winning all the stage games afterwards, right? So after some point, I have to win all of them. So this is what I try to formulate here. Player I wins in the repeated game if after a certain stage, she wins in the one-shot Fornefeld's game. And well, this payoff function is bounded, Borel measurable, and even tail measurable because of this condition that I should win for large enough stages. And oops, sorry. I will reconstruct a 0 equilibrium in the repeated version. So the interesting thing is that in the one-shot version, there's no epsilon equilibrium, as Mark Fornefeld proved. If you go to the repeated version of this game, then suddenly there is an equilibrium, even a 0 equilibrium. And the 0 equilibrium will take the following shape. We construct actually a run in this game. So it's a pure run. Everybody plays a certain action in it. And how does it look like? In stage 0, so in the beginning of the game, everybody plays action 1. This is what's happening at stage 1. At stage 0, I'm sorry. At stage 1, this will be the action profile. Now player 0 is playing the minority action. So at stage 1, we allow player 0 to win the stage game. Player 1 is still losing the stage game, player 2 is losing, and all the other players are losing. At stage 2, already 2 players are winning in the stage game. These 2 players, player 0 and player 1. And then 3 players will win the stage game, and so on. So obviously, if you go to infinity, then whichever player you take, maybe you take player 2, you see that after finitely many rounds, this player will win all the one-shot games. So his payoff will be equal to 1 on the infinitely repeated game. You can construct other zero equilibria in similar fashion. You can just fix a default action like the red one. It's completely random that you see here, action 0, action 1, action 0. Just write down anything you want. The only important thing here is that where my mouse is moving, that we write here the minority action so that player 0 is winning at stage 1. And here, where my mouse is moving, we should make sure that players 0 and 1 are winning by playing the minority action with respect to these actions here, right? So you can construct many zero equilibria, but they have the same pattern: play a certain run and make every player win in the end. The construction will be, the general construction will also do something like this, but this will be a little bit more complicated because we can only do constructions for a positive error, and also we will need punishments at a certain point. So I will go to the proof, and this is where I feel my own limitations as what I can explain reasonably. I will focus on the main line of the proof, the main ideas, and where the main assumptions are used. And there are many technical details that one has to take care of. I try to hide it as much as possible. It's not my expectations that I'm going to be able to explain everything exactly, but I think my hope is that at least I can explain the main ideas and what's going on here. This is the main idea in a very short view, and then I will split the proof into steps. So we have to prove that there is an epsilon equilibrium, so we just as well fix this vector epsilon in the beginning. And well, similarly to the game by Mark Fornefeld, we will identify a run. This was the run in that big table that I was writing down. This run I call X here, that gives each player a high payoff. In Mark's game, everybody was winning, but this is, of course, not realistic because not all games are win or lose games. We have payoff functions, and also sometimes it's impossible to give everybody the best payoff this player could get. But high payoff will mean that playerized payoff in the repeated game is at least some certain amount. What is this certain amount? This is something I will define later. This is a kind of min-max value of player I in the infinitely repeated game. It's not the usual min-max value that you could expect, but it's somewhat modified. And what will be the epsilon equilibrium? We will ask the players to follow this run, this action, this sequence of action profiles, and it gives them a good payoff. So there's an incentive already not to deviate. But still, if a player is trying something else and deviates, then of course the players notice this because a run, we know already what the players should do. And the players, the opponents, will react to the deviation and punish this deviator by lowering her payoff down to the min-max value that I was talking about, plus this epsilon for the player. So if you compare the two, this is what the player would get without deviation, and this is what the player will get at most after a deviation. And if we manage to do so, then a player doesn't have an incentive to deviate. But how to find such a run X? And what does it mean exactly, this min-max value? And that's actually the task that I have for the remaining 20-25 minutes. I don't know. I don't think I will need that much time, but
Janos?
Yes.
Since the players are playing mixed strategy, how can you detect the deviation?
So the run that I mentioned, thank you for the question. The run that I mentioned, it's exactly like a Mark Fornefeld's game. Everybody is expected or supposed to play a certain action, a pure action with probability 1. And then you notice immediately if a player deviates, it's like here, right? So look, this, like this one here, it's a run, right? I've wrote down one particular action for everybody. And if a player deviates from this, then we immediately see. And you can react at the next stage. Yes, it's actually a very good point. This is, otherwise this would be a much more problematic issue, yes. If I recall correctly, and Elon will enter problems like you mentioned, what happens if it's not pure, but I could be mistaken. Let me not mix up my mind with two talks. So now so we want to find such a run X, and we also have to tell what this min-max value is. And that's what I will start with. I will define first this min-max value, which we call finitistic min-max value, and the strategies behind them are finitistic strategy profiles. I already wrote down the characteristic feature of these strategy profiles. There are infinitely many players, so it would be a possibility that everybody is randomizing, right? Everybody could half-half on 2 actions. But we are only considering for our construction strategy profiles there where only finitely many players are allowed to randomize. I'm sorry for selectioning something with the mouse. So all players but finitely many will play pure. So maybe 2 players are randomizing, but all the other infinite players are playing 1 pure action. And we have very good reasons to work with these so-called finitistic strategy profiles. I will explain later. And I will define it immediately for the infinite game, but I will also have to deal with this situation for one-shot games, because what is a repeated game? A repeated game is a repetition of a one-shot game. So we cannot avoid discussing this situation for the one-shot game, which happens at a particular stage of the repeated game. And the step 3 is the one where I will hand wave a lot, see it as my shortcoming. This is the part where we will actually define an auxiliary function for each player. Let's call it DI. This DI is very similar to the function that Ron was talking about yesterday when he was talking about Martin's result for Blackwell determinacy. As you remember, player 1, it's not the player 1 for the repeated game, but it's player 1 from Martin's zero-sum game. It's player 1 from that game whose task is in every stage to name a continuation, or if you want, a fictitious payoff function. So this will be the strategy that is coming from such an artificial player. And here I will talk about how this auxiliary function is constructed. It's in the same vein as Martin's function, but we have to deal with a lot of issues, so it will not be exactly the same at all. But it has similarities. And then we prove that there is a desired run that we want to have, and then we complete that proof. So I will talk first about these finitistic strategy profiles where everybody plays a pure action, except perhaps finitely many players. So I already said what it is. A strategy profile sigma is finitistic if at each position, so whatever position you have in the game, you have the following property. All players, except finitely many, play a pure action. So this randomization, even if you want to consider it, the randomization is nothing more than a Dirac measure. So it puts probability 1 on one action. You could just as well think of one pure action simply. Why do we look at these finitistic strategy profiles? One main there are 3 reasons. One I did not mention. It's easier to work with them because there's less randomization. but that's obvious. I do not write it. The more important one, much more important one, is the following. If you look at a particular stage T, stage 0 or stage 10, doesn't matter, you can look at how many past histories you can have, how many positions you can reach with a positive probability at this stage. So if it's stage 10, how many different positions could we reach with positive probability under a finitistic strategy profile? Because this is finitistic, only finitely many players can randomize. We will have only finitely many positions that are reachable at time t. And that means that this little bit complicated measurability condition is automatically fulfilled in an essential way for our finitistic strategy profiles. So we do not have to worry about this. An additional property which is obvious, even if one player deviates from the finitistic strategy profile, after this deviation, we are still in the finitistic case, because even if this player decides to randomize, it's still at most finitely many who randomize at a certain position. And then we can define the finitistic min-max value, where the opponents are not playing any strategy. They are restricted to use a finitistic strategy profile. So it's the same inf-sup or min-max expression. The difference is here where I highlighted. And well, since this player's minus I could be restricted, this is, well, at least as much as the classical min-max value, but maybe higher. We can define the finitistic min-max in subgames in the same way, but this is the fourth. It's actually a property where. Wait a second. Oh, sorry, I was thinking of something else. This is the place where we heavily use tail measurability, the condition that the payoff function is tail measurable. So if you look at the min-max values, the finitistic ones, this is the min-max value from the beginning of the game, and this is the min-max value from an arbitrary position at an arbitrary stage. They are the same. And why? The reason is that because of tail measurability does not happen what happened until we reach the position P. It will not have an effect. This finite event doesn't have an effect on the payoff. So the players have strategically the same possibilities after a position than as from the original position of the game. The second step that I have is that I define these finitistic min-max values for the one-shot games. This will be an easier task because for a large part, this will be a repetition. So now I look at a one-shot game, think of the game at stage T. We have infinitely many players, they have their action sets, and well, I want to define payoff functions because for the single stage, because this will play this one-shot game an important role. Later on, this UI that I write here for the payoff function, this will be actually replaced with this DI that we will construct in the next step, but we are not there yet. So what happens in the one-shot game? We can still define finitistic strategy profiles for the one-shot game, only finitely many players randomized. These are exactly the same properties. I just kept it here for completeness, so I immediately skip this. And the finitistic min-max of this player I, it will be a small v to distinguish from the capital V of the infinite game. So the infinite game, it's capital V, the finite game is small v. This is the finitistic min-max of a player at in a certain one-shot game. And I would like to make 2 points. I was skipping it here, but we assume that this payoff function is bounded. But we do not need to assume that this payoff function, the one-shot payoff function, is measurable with respect to the topology on A. And the reason is that as long as only finitely many players randomize, it's just like before, this measurability condition that we had, the MC was automatically fulfilled. It's the same situation here. Only finitely many action profiles will occur with positive probabilities, so we do not have to worry about this. And this is not only convenient, but it's also very important, because later on we will have one-shot games where the payoff function UI is actually this D, and that's coming from something that is in some way similar to Martin, and we do not have any condition on the measurability of this payoff function. And so it's actually very important for our proof. For those who are interested in this detail, it's not important for the proof, but if UI, this one-stage payoff, was measurable, then in fact it turns out that the finitistic min-max is equal to the classical min-max when the players minus I are not restricted. So even if infinitely many players are allowed to randomize, then we need measurability, but then the players, even if infinitely many randomize, they cannot lower player I's payoff below the finitistic one. That's an interesting fact. It's all related to, well, I don't go into this now. So step 3, this is just one slide because it's immensely technical. This is an important step. What do? We construct a payoff function, which is an auxiliary, well, I should say function, which assigns to each position a fictitious continuation payoff, like Ron and Arkady were mentioning it yesterday. This is constructed in a similar way as Martin, but with substantial differences. So this is my single slide, and please allow me to be a little bit skippy. So in Martin's case, when we were looking at, it's in Ron's talk, actually yesterday, it's the zero-sum situation for the moment. I like to make a kind of comparison. If the payoff that this auxiliary game that is played with, so this is Martin's auxiliary game, not a repeated game or whatsoever. This is the auxiliary game that we are looking at. If the starting payoff Z in this auxiliary game is below the value of the game, then player 1's payoff in the auxiliary game was generating this small d. This is like Arkady said, the promise for the future, that for each position it has a promise what the value should be at least at. And if you follow Martin's proof, it has the following property, that if the function d is not decreasing in expectation under a certain strategy profile, sigma 1, sigma 2. So if today the d is giving this value, this is what the d will give you tomorrow. If it's not decreasing, it's a one-shot condition, then the payoff in the infinite game will not be below this z. It's coming from the fact that player 1, the auxiliary game, player 1 in that game is winning. What we do, but this is just a part of the entire story. If for each player, fix a player, we construct a payoff function for each player I separately. So if you consider one fixed player and you take a payoff Zi, which is less than the finitistic min-max value of this player in the infinite game, then you can construct a fictitious payoff for this player that attaches to each position a continuation payoff, and it has the following property. If with respect to the finitistic one-shot min-max value, this has this non-decreasing property, to put it that way, sigma here is just some kind of finitistic strategy profile, then this finitistic strategy profile is not, will have one interesting property in the infinite game. It will guarantee that player I's payoff in the infinite game is at least this Zi. So we can relate the payoff guarantees in the infinite game to one-shot games. And not only from the initial position like in Martin, because this was a payoff guarantee in the repeated game from the initial position, we can also do so for each position. So basically, this will be a good payoff in each subgame for player I. And I'm sorry that I cannot explain this in more detail. I think that's for now. Last step of the proof, and then we are done. How do we construct the desired run, and what is the completion of the proof? And part of it we have already done, but some part of it not. So what do? We remember that we have some kind of fixed positive epsilon vector. For each player, the error is positive. And then we take some kind of zi. This is once again a payoff that is a little bit below the finitistic min-max value of the player. And then we take the function that was constructed before. And we also take a default action for each player, which will play an important role, just like in the game of Mark Fornefeld. So now we construct a finitistic strategy profile sigma. This is not going to be the zero equilibrium. This is only helping us to find the run that we will use for the zero equilibrium. So what happens in the strategy profile in each position? We ask if it's this position is at a certain stage t, just like in Mark Fornefeld's game, we ask all players whose index is beyond that stage to sleep. They are not doing actively anything. They just choose their default action in this strategy profile. The first t players will be active, and these players will play according to their function di that was constructed before. So they can choose actions, but whichever the actions they choose, we will combine, of course, with the default actions of the opponent. And this continuation payoff will tell player I how good he is doing in this one-shot game. And since this is a one-shot game with finitely many players in this sense, this will give us an equilibrium. So if you look at it, this is looking at it stage by stage. If you look at it player by player, player I is waiting at stages 1 up to I-1, and suddenly he wakes up at stage Y and starts to choose actions in a strategic way. Now, I will be quick. Because of the construction, all the players are getting good payoffs here. This is because the players are choosing good actions in the one-shot games according to DI. So everybody is getting at least his finitistic min-max minus the corresponding epsilon. Now, because it's we have Levy's 0 one low, this means that the payoff will be high with probability 1. So this property is not only true in the beginning, this is important, but this is true in every subgame, right? We were constructing a subgame good payoff function. So under sigma, every player will get a good payoff, but not in expectation, but with probability 1. And this is where the point where we use that there are countably many players, because if it's true for countably many players separately, then if you take intersections of these sets, it will still have a probability 1. So that will mean that each player will win simultaneously, and then you can find a run that satisfies this inequality. And this is the run that we want to have, because now if the players follow this run, then they get a good payoff. And if a player deviates, then we can still punish this player by moving to the finitistic min-max from the next stage, which is still the same because the finitistic min-max does not change across subgames. It's because of tail-measurability. Well, this is the main theorem. I apologize for everything that was not clear. This is the best I could do. That's the only claim I have about the proof. Nothing more.
Thank you, Janos. Actually, it was great.
I couldn't do it better. I'm sure many others could have
Your
done it
lecture
better,
was
but
great, and all lectures so far were great. So thank you all. I have a comment or a question. The theorem here speaks about an epsilon, a vector of epsilon equilibrium.
yes.
And indeed, as you show, that Pelek's example doesn't work for the epsilon that is fixed, but just
Yes.
a comment. If you take a summable sequence of epsilon i's, then the Pelek's example is a counterexample.
Excellent. I completely agree immediately. Yes, you have. Yes, that's true. Yes. If epsilon, the vector epsilon, say the coordinates go down quickly to 0, that's what you mean, Abraham, then you
Yes,
can construct.
the sum of the epsilon I is less than infinity.
Yeah. Yes. Yes. Yeah. So that's true.
Yeah.
Yes.
So I have a question. So if you do like the boring standard economics, repeated games, discounted, finally many players, it's straightforward to relate the repeated game payoffs, yeah, up to normalization, the convex hull of the stage game payoffs. And this one example, you get in some sense a payoff which is much better than everything that you can get in the stage game. Can you say anything general about how like repeated game payoffs look like?
So what I could say, let me start with this one, because this is already something I can mention without too much thinking, and I will come closer to your question as well. So first of all, you could think of some kind of folk theorem type of thing, right? Like Galit was talking about. What we can do is the following. So I just jump back one slide. So we were constructing a run X or a play X, which gave each player a good payoff. And then we could construct an equilibrium, epsilon equilibrium, that was giving the payoff corresponding to X. Now you can imagine that there are several such runs perhaps in the game. Then we can convexify the corresponding payoffs by these joint lotteries that Galit mentioned in the previous talk. You could assume that we use stage one, in which many players will, I don't know, 2 players or more, they will randomize, and depending on the outcome, the players will decide which run, maybe X or X prime or X double prime, they will follow in the future. And because it's a tail payoff, this jointly controlled lottery is not destroying the payoff, so you can just use stage one for doing this, and then with certain probability you will play the X profile, and with certain probability you will play the X prime profile, so you can convexify these payoffs. Now coming closer to what you say is that there is a stage payoff. In this talk, I was talking about, or in the paper also, we talk about the more general case where we do not really have stage payoffs here. We define the payoffs immediately on the infinite runs of the game. So if once you talk about stage payoffs, suppose there is a stage payoff, then you still have to define what the payoff is going to be in the infinite game. Is it the long run frequency of the actions, or is it the long run average payoff that you are considering? So if you talk about stage payoffs, you still have to say what the players will get in the infinite game. So my answer would heavily depend on which aggregation you choose.
Okay. Because
I hope I answered the question. I wasn't sure because I missed 2 seconds. I couldn't hear the very beginning, but so I was.
No, because it seems like in this game, Wonneberg's game, like the repeated game payoff, say under lim sub of means or something, is still much better than every stage game payoff, which is. So that I think was surprising. Thank you.
So Janos, I was thinking about this during your talk, that I remember when first time I learned this repeated games, we started with preferences. So what if you define, I don't know how, and I don't know whether it helps or not, the define tail measurability somehow, so tail measurable preferences, and then you just choose a representative utility of a payoff function, which is perhaps tail measurable. So have you been thinking about this kind of approaches to generalize your results or the notions you use?
I guess it's a very good question. I also know papers where they indeed do not look at payoff functions, but a preference relation on the outcomes. Yesterday, just as an example, there are many other papers. This is one example. The paper that I referred to by Stéphane Leroux and Arno Pauli, for example, in that paper, or maybe a companion paper, I'm not sure, they really examine situations. In our case, the difficulty that I see here is that suppose we only have a preference relation on the infinite runs. What happens if I play half today? Then one run will happen with probability half and another run with probability half. How do I measure probability measures on the outcomes with each other? So as long as you construct pure strategies, there is something to say, but in our construction, the main path is still pure, although to reach this main path, we are already using mixed strategies to prove that there is one. So even to get there, but suppose that you have such an X, then in the punishment phase, the players still have to randomize there, and then I think what you say is a good question, but this will enter the picture, I think, at several points. What happens if you get probability measures over runs, because then so there's literature on this one as well, but I cannot give a completely satisfactory answer because of this, I think.
Okay, thank you.
One comment to Miklos' question. If you start with preferences, the issue will always be, what do you mean by the epsilon equilibrium? Because if you, in this case, you have to start with preferences and show that there is a kind of a unique utility function that represents this preference, and then, or canonical one, and then you would be able to speak about epsilon equilibrium.
Yeah, thank you. Yeah, see. Yeah, so we lose this notion. If we go to preferences, we lose this notion of epsilon, the closeness, and then we cannot say anything. Thanks.
You can say, there are cases by which you can say.
Yeah, you can introduce
some.
Careful,
yeah. You have to impose maybe a few more axioms on the preferences so that you will have a kind of a canonical representation that will enable you to speak about epsilon equilibrium or epsilon optimization.
Thank you.
Yes, that's also true, yes.
There are no more questions, and thank you, Janos, again.